The Archimedes principle states that when an object is totally or partially immersed in a liquid or gas, the upthrust on it is equal to the weight of the liquid or gas displaced.
When an object is totally or partially immersed, you said in a liquid? You said in a liquid or gas?
Yes.
What single word can we use to replace those two?
Fluid.
Yes.
Fluid.
Yes. Instead of using liquid or gas, you just say fluid. Partially immersed in a fluid, comma, it experiences an upthrust that is equal to the weight of the fluid displaced. Now, this statement here is very important, but we need to understand what it means. If we say something is partially or wholly immersed, what does it mean? How do you simplify to somebody who doesn't do physics, to a lay person? If I say totally or partially immersed, what do you think I try to mean by that statement, those two words?
I think it means that you can either put it partially, like when the body object is partially in the fluid.
Just part of the body, or the entire body is fully immersed in the fluid. I want to do, if this is the liquid, there is some water inside here. I want to get some object. You have a pencil. Do you see this piece of chalk? If I put this piece of chalk like this, some part of the chalk is outside, the other part is inside. It means this is partially immersed. But the moment I get this entire piece of chalk, and I drop it in, are you able to see the piece of chalk? It is fully immersed in the liquid. It is in the water, fully immersed in the water. So when it is fully immersed in the water, or if it is partially immersed, Archimedes' principle will apply. But it says, the principle says, first of all, that piece of chalk I was holding has weight. If it has weight, like you people have weight, objects have weight, anything that has mass must have weight. If it has weight, it means what happens when I put that piece of chalk in water? If the level of water was here, was this, let me say this is level 1. If the level was at level 1, and then I somehow put this piece of chalk like this, what will happen to the level of water? What do you think will happen to the initial level? Does it still stay level 1 when I put in something? What happens to the level? Does it increase or it goes up?
The level of water increases.
The level rises. We can have something like this. So we have level 2. Now that level 2, does it mean we have added water into that can? Did we add water?
No, it's just
the body, like.
It is the body that has made the level to rise. Now, what we want, this Archimedes principle does not actually cater for the other first level, the initial level. Archimedes principle is basically looking at that level, that new portion, let me say volume of level 1. If I get the volume of the water that has been displaced, this part here shows the displaced water. So volume of the displaced water is level 2 minus level 1. Now, what we want for us in Archimedes principle, our target is to discuss that displaced water. The whole science of Archimedes will go to that displaced water. If you can be able to get that displaced water, by the way, what method can I use to help me collect that displaced water? Because in this principle, they are saying it must in a fluid, it expresses an upthrust that is equal to the weight. So the weight they are talking about, let us first discuss that weight. Are they talking about the weight of the initial water that was at this level? The initial water was at this level. Are they talking about this weight here, the weight of this water?
No.
What weight are they talking about?
No.
They are not talking about the initial weight. Neither are they talking about the new weight. Because the weight of that water will not change. If you had 2 kilograms of water in this can, even if you put in some other object, it will still remain 2 kilograms of water. So the weight will not change. But what will happen is the displacement. There will be some water that is displaced. So if I'm able to collect this water that has been displaced, this one, if I put it in this can, the entire Archimedes principle is basically discussing this water here. And they are saying it's equal to the weight of the water displaced. So the weight we are talking about here is the weight that we are putting here in this part. Am I trying to be clear to the statement? We have totally or partially immersed, we have the upthrust, and we have the weight. This weight here is the weight of this water that has been displaced, but that water was partial, was part of the original. We have not added any single volume of water. It's the same water that we have, only that we have displaced it. And this weight here, if you are able to measure the weight, what methods can we use to measure the weight? Do you know any method we can use to measure the weight? Who can tell us any technique we can use to measure the weight of that liquid that has been displaced? What method do we use?
Using an overflow can.
Okay, Auntie. Okay, overflow can is okay, but it helps us collect it the way I've put it there. Assuming we have already finished collecting it, and that water is here. How do we measure its weight? Because the overflow can does not measure weight, it just helps us to collect it in some other can.
It's a measuring cylinder.
Measuring cylinder. Okay. Hey, measuring cylinder, what does it help us to measure?
The weight of the
measuring cylinder. Measuring cylinder is for volume. Measuring cylinder is for volume. In physics,
the weight of air minus the weight of water.
Weight of what?
Weight in air minus the weight in water.
Hey, see now there you are getting the weight of the other object that we are talking about. First, we are talking about this water. What is the method that you can employ to help you measure weight of that water in that can? If they give you water in a can, okay, if they give you water in a cup at home, then they ask you, can you help us measure the weight of this water? What do you do?
You get the weight of the can without the water, then the weight of the can with the water, and the mass of the can with the water, then you subtract.
Okay, so we get the weight. Which one we subtract? Weight of the can with the water minus weight of the empty can. That's what you're saying. Weight of the can plus the water minus the weight of the empty can. Okay, this one will give us the weight of that water, the displaced water. Are people following? You get the, but now she has not answered, only she has given us a formula. weight of the water plus the can together minus the weight of the empty can. You must have measured that empty can to get the weight of that water. But my question, how do you measure weight? The formula is very correct, but how shall we measure weight? Clarissa,
So you use
Babi.
spring balance.
Oh,
So you use them, and then you multiply it, the by the acceleration due to gravity.
We multiply by g. But what did you say? We use what? I didn't hear the first statement.
You get the mass of the can plus.
Hey, how do you get the mass? What device do we use to help us get the mass in physics?
Measuring scale.
Okay, you can get a measuring scale or a weighing or a spring balance. Somebody talked about a spring balance. There are two balances we normally discuss in physics when we compare weight and mass. There is a spring balance and also a beam balance. A spring balance and a beam balance. Of these two, which one do we use to measure weight? Spring balance or beam balance?
Spring.
Spring balance.
It's a spring balance. We use a spring balance. If you want to measure mass, for mass, that is where we use a beam balance. That number normally comes in section A. They can give you objectives and they ask which of the following is used to measure mass. You have to remember, for mass, it is the beam balance. Beam balance is for mass. While spring balance is for weight. Spring balance is for weight. Okay, yeah, this one was just a recap of what measures. So it means if I want to measure, let me answer somebody's student call. I was saying that we use a spring balance to measure the weight. Now we want to break up this statement. Our major target is to first understand the principle itself, because most people make mistakes. Remember, in paper 2, they can ask you to verify. For those of you who have seen those numbers, verify Archimedes principle. Now, to verify means you need to go back and break up this statement into the portions that you're trying to break up. Here they are saying it experiences an upthrust, and that upthrust is equal. They are see these statements. Upthrust is equal to the weight of the fluid displaced. Upthrust is equal to the weight of the fluid displaced. Now here we have seen that we have collected the liquid that has been displaced, and after collecting it, we have gotten its weight. Now after getting this weight, we need to compare this weight. We need to compare the weight with the weight. Some of your friends have failed to join. Okay, who was telling us about upthrust? We have seen how to measure the weight. Now our other part is to measure the upthrust. And I was asking, how do you get upthrust of an object?
Mass times acceleration due to gravity.
Mass times acceleration times density.
That is how you get upthrust. What formula do we get? By the way, what is upthrust? That's the word upthrust.
Apparent force in weight of a body.
Upward force.
Exerted by a fluid
in an object.
Upward force exerted on the body. The upward force exerted on a body placed in a fluid. The upward force, if this is the particle, there is that upward force. There is that force that acts upwards. It's what we call upthrust. Now I was asking, how do you get upthrust of a body? Somebody said you get mass times G. Okay, that is getting weight, eh? But how do you get upthrust? Just upthrust. Upthrust is equal to
Weight in air and accessible.
Weight of that object in air minus weight of this object in, if you are using water. Water, you can say. So this is how we get upthrust. If this is the way we get upthrust, let us just make it general, a free. If this is how we get upthrust, I want people to be careful with these statements we are doing. This is upthrust. And this side we are getting the weight. Remember, this side, we are getting the weight of the displaced water. Displaced water. Weight of the water plus can minus weight of empty can. So we shall get, it means when you look at this side of upthrust, when you look at this side, it means we shall get our spring balance. We shall get the spring balance and weigh the object in air. We shall weigh the object in air. Then after weighing the object in air, we shall also weigh the same object while placed in a liquid, like water. If this is the spring balance, so we can get the weight in air. Then after this weight in air, we get the same spring balance. This is the spring balance. Then we get this object and place it in water. So we have two portions. We first get the weight when it is in air, just open in the surrounding. Then afterwards, we take that object with the spring balance and immerse it in water. When you immerse it in water, again check what is the new reading of that spring balance. The reading of the spring balance, a spring balance has just a pointer. I would have come with one. You get the weight in air, the weight in water. When you get these two, if I ask you a question, which of the two do you think is higher than the other value? Is it the weight in air being higher than the weight in water, or the other way around?
The weight in water.
The weight in air.
The weight in
Air.
Air.
The weight in air is always greater than other values. Objects reduce their weight. Every time you put an object in any other liquid, its weight will reduce. That's why in our formula for upthrust, we always start with weight in air. So weight in air is higher than the weight in the fluid. Since we have used water, let me immediately put the word water here. So after getting this, we have gotten our value in air, we have gotten our value in water, so we have an answer. We have an answer here for upthrust. The statement said, don't forget, we are trying to verify Archimedes' principle. The principle said that this upthrust that we are talking about here, this upthrust is equal to the weight of the displaced water. So how do I now verify that what I'm doing is correct? That now I have verified Archimedes' principle. What do you think I'm going to do? After I have this figure, I have an answer for upthrust. I also got my answer for the weight of the displaced water. So how do I verify now? I have two answers. I have gotten upthrust, I have also gotten the other weight. How do I verify my statement? Who can give us a conclusion? on what you are going to say.
Teacher, the answers should be the same.
Very nice. Thank you so much. The answers must be the same. The answer you get here, that answer will be in newtons. If I get answer X as upthrust, remember you have gotten upthrust using a different method. Our method was using a spring balance. We weigh in air, we weigh in water, and subtract. So we have our answer here. Then on this side, we got the liquid. We first measured the weighing can. I mean the can, the weight of the can. Then when we got our water that was displaced, we also measured the two now, weight of the can and the water. Then we subtracted to know what was the weight of the displaced water. So this answer must be, this answer should also be X. This X you have here must be the same as this X. The moment you have similar answers, then you have verified the principle. Upthrust on this side must be equal to the weight of the displaced water. This is how we verify. Verification means you're trying to prove. So that if my answer for upthrust is X, it will be the same answer for the weight of the displaced water. If this is true, then we have verified Archimedes' principle. Am I trying to make myself clear?
Yes,
Teacher.
Somebody is saying she's confused. I don't know. Can you please ask where you're confused from?
Yes. So
Where are you confused from?
from the part of where you're saying that the answer you get for upthrust is going to be equal to the same weight of displacement. In a question, does it mean that the two are going to come together in order to like prove that the Archimedes principle is correct?
Yes, the two, okay, it depends on what they're asking for. In this question, we are trying to answer a number where they say, describe an experiment to verify Archimedes' principle, verification. After knowing how to state the principle, then the examiner asks you, but how do you know it is a true principle? How did they come up to say that the upthrust is equal to the weight of the displaced water? So in the question, they will not give you the similar answers because there are some calculations where they just give other things depending on what they are asking for. But for verifying, if they ask you an experiment to verify, that experiment must be in two parts. One part should be on how to get upthrust. This side here, weighing in air and weighing in water, and you subtract to see the answer you get. After getting that answer, you keep it on the side. Then you do part two of this, getting the object, place it in water, and collect the displaced liquid. When you collect that liquid, also get its weight. Then you compare the two answers. And the statement says, when you compare the two answers, they must be the same. If they are the same, like what you have said up here, if they are the same, then you have verified Archimedes' principle. We are just verifying, we're not answering a calculation. Calculations can ask anything they want. They can ask for upthrust alone, they can ask for the other weight. But for verification, it will come through this kind of question. Let me pass share for your screen as I answer somebody on the. You check out that whatever, the information where they are verifying, read through the steps. Are you checking the steps? Weigh the object in air, then you weigh using a spring ballast object WA, then weigh the object in water. Those first two steps are to help us get the upthrust. Then you also get the weight of the displaced liquid. When you get those ones, then the answers must be the same. It is found out, if you check here, it is found out that weight of displaced water, this statement here that they are making here, it is found out that weight of the displaced water is equal to upthrust. Thus, Archimedes' principle. Very few steps, as long as you understand what you're writing. Are we together, people?
Yes, yes, teacher.
Because I want us to do some calculations that involve this principle. If you understand this principle, then the other part of the law of flotation becomes very direct. Because this one is the one that has challenging bits. Most people don't understand this. Okay, now let me just use the same page. We go to Now there is that example one. Let me write it on the board as you copy it from the diagram, from the screen. We are copy example one and try it out before you check the solutions. I think, let me first hide these solutions. A glass block weighs 25 newtons. Weighs 25 newtons, full stop. When wholly immersed in water, the block appears to weigh 15. The block appears to calculate the upthrust. So can you calculate that upthrust?
El marinero. El marinero. Marinero. Sem marinero.
What answer have you got?
10.
10 newtons.
10 newtons. How have you gotten the 10 newtons?
Subtract the weight in air minus the weight in
water.
Okay. Somebody has subtracted. So we got up thrust, weight in air minus weight in water. Weight in air was 25 minus 15, and we get 10 newtons. So this is the up thrust. Now let me see if they ask you, if this is the up thrust, if they ask you part 2, what is the weight of the water displaced? Part 2. Calculate the weight.
Take question
Weight of the displaced water. What would be the answer for this?
10 still.
The answer will still be 10. Who can give us a reason for that? Why do you also say the answer is 10?
Because
Upthrust.
upthrust is equal to the water
Upthrust is equal to the weight of the displaced water.
That is Archimedes' principle. So there are sometimes when they ask you questions that do not need calculations, but they just require you to remember the principle itself, whereby you just have to relate the two answers and then give the examiner what they want. So part 2 of the weight of the displaced water is also there, the same figure. Let me see what was their part in their question. As if there was part B. Let me see what was part 2. Okay, there's just example 2. Example 2. Okay, you copy that example 2. A metal weighs 20 newtons in. Let me hope the other number is okay now. This first number you have done. Any person is still having challenges for this part A, number 1? Are we together with number 1? Okay.
Yes,
You got to number 2. Example 2. A metal. You got to example 2 now. Some of your friends have failed to join using the e-learning platform. Please, you guide them. During your WhatsApp messages, when you are chatting, you chat as you're guiding each other. Don't chat those things. Hey, wait, teacher was smart. What? Chat useful stuff.
LOL.
Money. Hey, the money. A metal weighs 20 newtons in air. A metal weighs when wholly immersed in water, and on 15 when fully immersed in water. Calculate the Roman 1. So somebody should have already finished part A. What's the answer for part A?
Yes.
5 Newton.
5 Newton.
Okay, fine.
5.
Okay, if you have a pencil, you mark yourself there.
Okay.
Newton.
Okay, you mark 5 newtons, then you go to part 2.
5 newtons.
Okay, 5. And why are we saying 5?
Archimedes principle.
Very nice, Archimedes principle, because the principle says the abstract is always equal to the other. So part 3.
We don't know.
Part 3. Some answers?
5
Teacher,
times
part
10
3, yeah?
exponent.
Somebody has
negative.
3.
Part 3. 5 times 10 exponent negative 4. Meters cubed.
Okay, I'm waiting. Other people are still working out.
What is she saying? Teacher, for me, I have 10. Right?
You have 10, eh?
I have
Yes.
nothing.
Somebody has nothing. Nothing, you start working out. Get your paper.
For me, I was saying the answer for part 3, the volume.
Hey,
Part 3, the volume, we don't know.
what you calculate? That's what they're asking for it.
We don't know.
Teacher,
No.
0.005.
I think I've taught you, I've already taught. That's why people are getting answers. You
No
try
one's
your
done
level best. You try your level best.
Some of us don't know.
So we have tried it as Joe.
You are going to use, you see, did you get, those people who have tried and failed, do you have part 2? What have you written for part 2?
5 Newton.
Okay, how did you get 5?
I subtract.
Subtracting Newton minus 15.
Afterwards is equal to that.
Okay, that's the very statement I want. Upthrust.
Because
Okay, I'm assuming part A, you have gotten 20 minus 15, 5 newtons.
15.
5 newtons, eh? That is part A. Now part B, you have told me upthrust. We are just using the principle. Upthrust is equal to the weight of the displaced water. Now my statement is, from every time you are going to work out such numbers of Archimedes principle, always remember that statement you have written in part B. Now from that statement, we are going to break up the other side of the weight. Who remembers the formula for weight? What is the formula for weight? How do you get weight? Mass. You see? After somebody is even telling us the answer. It is mass times G. Do you remember that one? But in this statement, this letter M represents mass. If I may ask you, it is mass for what? It is mass of what? Is it mass for the can, mass for water? It's mass for what?
The displaced water.
It is the mass of the displaced. Be careful with that statement, mass of the displaced water. Because the weight we are talking about here is weight of the displaced water. So, again, we can break up that letter M. Do you know the formula for mass?
Yes.
What is the formula for mass?
Volume times density.
Volume times density.
Times volume. Let me first answer somebody here. Somebody who was stuck the other time, I think now you are seeing that the answer can easily be good. This letter represents density. This V is for volume. These two letters were for mass. Mass is density times volume. This G is this one. Now, out of these letters, what do you have this side? Do you notice that this side, I'm going to put 5. Do you agree? And this is upthrust. Already you have told me upthrust is 5 from this part. But now, out of those 3 letters, density, V and G, what are we looking for? In their question, look at this.
Now V.
Yes, now V. So can you make V the subject?
Answer is 5 times 10 upon negative 4.
Young girl.
The density of water is 1,000. This one is always given on the front paper. Anyway, I always look for, if it is water, it is 1,000. If it's another liquid, don't put 1,000. Check in the question, they must have given you that density of that given liquid. But for water, they normally don't give it on the question, but they put it on the front paper. Before the questions are started, they always put some of those constants. So density is 1,000. Volume is what we don't know. What is delta G?
10.
10. So you get your V. Are we together?
Density is always
Yes, teacher.
Somebody who had written nothing, now have written something.
Yes.
Are you happy?
Yes.
very. Density is always 1,000.
No.
That is for water. If the question says water, if the question says water, it is 1,000. But other questions will say oil. Whichever liquid they give, in the question they will give you what to use. So you don't have to cram only for water. By the way, don't even cram these densities. They always give. First in physics, unlike other subjects that make you suffer, first we don't make people suffer. We give all the things that they want.
Okay.
Because we are the queen of science.
Okay. Teacher,
Wanji?
excuse me.
Yes.
I had gotten my answer 10 in a different way. I just want to ask if it's okay the way I did.
You have got
So
your answer in a
what I
different-
did, I don't know if I did. Yes.
What method have you used?
It was some fake method, but I had gotten 15 minus 5 equals 10. Like
15?
15
From the weight in water?
yes, and then the 5 from the weight of the displaced water. Does that make sense?
I think, okay, I've not understood that method, but let us go with this one. Now we have used it. It makes life easier. You also copy this. You can take a screenshot of this. You write it as your solution, because this one is going to help us work out other numbers. Because it's the principle, the Archimedes principle technique. Now put in what? In figures.
Okay, teacher.
Now we are on the next number. This one, people should work it out. You should not have anybody saying, I have nothing for this number. What I'm going to put, yes?
Do you have to write that volume in standard form?
You can even write it as 0.0.
Yeah.
0.0. You can write it like this. Any method you want. 0.000. How many zeros?
Enough, 5.
Then you put that, but the units must be meters cubed. So you can either write it like this or you write it like this.
Okay, thank you.
Depending on how you want it. Now, this number, I want us to see, you have to work it out very fast. At least you have gotten the idea of how to handle Archimedes principle. It is there. It is a, let me see out. It is example number 3. Just next, like the bottom part. Just example 3. Let me write it also. An iron cube of volume. This is you use the board. Calculate the upthrust in each case. Any answer?
Eight Newtons.
That is for part A, for the water.
Yes.
Okay. Any other person with the same answer?
Yes, teacher.
Eight Newtons.
Okay, you got part B.
6.4.
Somebody has 8,000. Somebody has 8 Newtons, somebody has 8,000. So
8 million.
80,000.
I have 8 million.
80,000.
Have nothing.
Shall we have 80,000?
we are going to work it out. 8,000 for part A or part B?
A.
Part A.
We have
Teacher, please help work out.
Let people first try.
Then
Do what is your
64
answer?
newtons. 64 newtons on part B.
60. Okay. Each person give your answer in that when you start working out. Give your answers ready. When you start working out, you compare our answers and your answers. We are giving ourselves one more minute. 1 more minute to that everybody gets chance. Please, everybody must be trying. When we say 1 more minute, don't relax and take porridge and say, let me wait for the teacher. You'll be trying out.
Shall we have 8,008,000?
Okay, 8 million, that is for part A.
Yeah.
and 8,000 for.
Okay. Yeah.
6.4.
6.4. Okay.
6.4 part B.
Okay. I'm happy people are trying out. That's very good. Very good. At least if you try out, by the time we start our calculations, you will be easily following. And Vinny. Vinny, you can slaughter that chicken. Slaughter. You need chicken soup for COVID.
Yes.
Okay, let us now try it out together. If you get the best technique for part A, part B becomes very simple. Now, what we have been saying, by the way, if you notice, all these numbers are basically applying the principle. So if somebody understands the principle, then someone is saying, teacher, chicken. If somebody understands the principle, all these numbers become very simple. I've seen people complaining, we don't understand the fluid mechanics. This part is called fluid mechanics, mechanics of fluids. But because the challenge is, they don't want to understand the principle. They only want to cram. When you make somebody stand somewhere there, even if you tell her, close your eyes and state the principle, they will state comfortably. But then ask them to verify it. They don't know how to verify it. Then when you ask them to do some calculation that involves that principle, again, they will say we are stuck. It's because, we don't blame any person, but it's because people tend to cram. And I insist and encourage you, don't cram principles, just understand how principles are applied. So for this number, for part A, for me, even before I do anything, I first write the principle. Principle says, up thrust is equal to the weight. That is what I write first. Weight of displaced. This one was what? Water. Part A was water, displaced water. So if they're asking for upthrust, is what I will leave. Upthrust like that. Now, the next part is to write down, how do I get weight? How to get weight? Because in their question, they have given us volume. Now you might ask yourself, where are we putting volume? But you remember, volume only comes in when you have written mass. Like this. And where you have mass, you put density times volume times G. Those are the steps. All the numbers always follow like this method, this way of working out. First of all, we are discussing water, and I told us water has a density of 1,000. So where I have this symbol is for density. If you don't remember this symbol, then you write the whole word density. There's no problem if you don't remember. So 1,000. Now, what is the volume? The question is, what is the volume? Volume. Let me just answer currently.
Every time answer. Why? Too much urgent.
I know, right?
Anange, this call.
Mukazi, ngosa nnyo. Nani yena? Gwe.
During parents' meeting, parents are quiet. Now I hear making noise.
Why? The good thing your father came. Parents' meeting. Timekeeper. When does the timekeeper? Timekeeper. How many minutes?
The challenge, I think the challenge was on the volume. How will this be? Because they gave us, according to them, the volume is 800.
800.
The volume is 800, but centimeters cubed.
Yes.
Remember, we don't use cubed. We don't use centimeters in our formula. In our formula, as use meters cubed. Now the question is, how do you change centimeters cubed to meters cubed? You divide or you multiply?
Divide.
Because if you remember, 1 centimeter is 1 out of 100 meters. So 1 centimeter cubed is 1 out of, if there are 3, then you write also 3 times. You see, 3 means 100, another 100, another 100.
Teacher, what? Aren't we supposed to be 6 zeros?
Huh?
You've written.
Yeah, 6.
Outside we bring the zeros time.
1, 2, 3. There are 6.
Yeah.
So it means our 8,000 has to be divided by 6 zeros. This is how you convert to meters cubed. So it means our
0.0008.
let me first write it the way it is supposed to be. 1, 2, 3, 4, 5, 6. Now times this last 10, the one for G. So this is how you should have gotten your answer. For those who have done this, what is your answer?
Something.
8 newtons.
So that also have got 8 newtons, eh? Because this is 0 and it goes with this.
Yes, we are there.
This is 0 goes with this. These are 3 zeros.
Newtons.
Yes. So the answer is 80 newtons. So that's how you should have gotten your answer.
Thank you, teacher.
But now you work out part 2 now in the right format. Part B.
Yes.
Yeah.
What I say?
0.0064.
First wait and
Yeah, everybody can first just use the next 1 minute to pick out the correct answers.
Zero point zero zero six.
Yes.
Okay. 0.00.
Just 6.4.
0.0064 newtons.
Now you have different answers. We're sorting the
Just 6.4 newtons.
0.64 newtons.
sort out yourselves. Which one is the right answer?
6.4.
6.4
Now I
.00
changing minutes. Problems. Changing
4.2.
units.
Don't change the
6.4.
don't change the volume.
No upthrust. Yes, start with this method. I start by writing this. I don't want to suffer.
Okay, don't suffer.
5 out of 10. Just say half.
So what was the density?
0.8.
0.8.
I
Yeah.
think the challenge
0.8.
the challenge was how to convert grams per cubic centimeters. 0.8 grams. How do you convert this to kilograms per meter cubed?
Oh my lord.
Multiply by 1,000.
Yes, very nice. Always multiply by 1,000. Senior one, you have forgotten senior one. Whenever you are converting from grams per cubic centimeters to kilograms per cubic centimeters, always multiply. By now you people, you be careful with this. I remember the other girl was making a mistake. What about if I'm converting this? Maybe this is what was confusing. If I'm converting this to kilograms, what do I do?
By 1,000.
Divide by 1,000.
Grams to kilograms, you divide.
Divide.
This is confusing. Somebody thinks that even this one, because it is starting with grams, that we shall also divide. This one has some other letter, some other unit, cubic centimeters. When you do the physics and mathematics, the one that has grams per cubic, you multiply. But the one that is only grams, you just divide. I don't want to go through that mathematics, but don't make that mistake. If there is a cubic centimeter, that's when you multiply. So here, our density is 8,000. The volume, we have already seen the volume was this. This is 800. These are 6 zeros. 1, 2, 3, 4, 5, 6. So those two have done like this. What is your answer? How many zeros?
6.4 Newton.
6.4. This
6.4.
6.
6.4 newtons.
Now, those four had made a mistake. What was your? I mean, I got wrong answers. What was the mistake?
We had not converted.
We did not convert.
Hey, always be careful with these units. The units must be
0.8 kgs.
They must be standard units. Kilograms per meters cubed. Where you see any grams, you have to convert to standard units.
Okay.
We have 5 minutes to the end of this session. Our sessions end at 10:30. Then you charge and make some chai at home for your parents.
Tells you.
Then the 11:30 will resume. Hey, you don't make.
The other ones to make us.
So we already have.
Guys, you're making you're slimming for what? You should take chai, bushera.
Yeah,
We already taking it.
Never.
Shouldn't slim. When you slim, people will leave you there. You float.
Nothing.
We shall float.
Don't say I didn't warn you.
Shall tell you show it now.
It's the fat one.
Who shall leave?
Okay, maybe This one, you just copy it up, you try it in your free time.
Okay.
Which one?
The one that has example.
Which one? You're
The one that has
scrolling.
What if you don't get?
The one that has example 3. Hey, okay, should be this one. Let me highlight it somewhere. The one I have highlighted.
The question.
The question is an iron cube.
Where is that you've highlighted?
Hey, the one that has an iron cube, mass 480
Example
grams.
3.
I have even highlighted it. Somebody should be able to see it. An iron cube, mass 480 grams, 480 grams, and density 8 grams
Mass
per cubic centimeter. It has mass 480 grams and density 8 grams per cubic centimeters. Is suspended by a string. Is suspended by a string so that it is half immersed in oil. Suspended by a string so that it is half immersed in oil of density, half immersed in oil of density 0.9. Half immersed in oil of density 0.9 cubic centimeters. First of all, find the tension in the string. Find the tension.
There is the tension the same as upwards.
Yes. What is the upward force? That's another way of asking for tension.
Teacher, now when the units are like the same, you also have to change.
Have to change. You have to change.
Solo is a must to change.
Hey.
Oh. Yummy.
Find the tension in the
string.
I want to see. Our next lesson, we shall look at the Archimedes principle and relative density things. We shall compare relative density items. Okay. I want. If you get other questions, you come with them. You can inbox or you can share on WhatsApp. In that, by the time we come back, everybody must have tried. It's better. You see that it's very good for you to try before the lesson, such that you have answers, and we just compare our answers. That's the best way we should revise our work. Okay, I wish you the best. Thank you so much for attending this lesson. It has been a very nice lesson, and I have recorded it. I will forward it on your platforms on my YouTube. By the way, when you go to the YouTube, you go and subscribe. You press the button. It is always at the bottom there, where there is that word subscribe. It's normally in red. Please, you press that button.
Which channel?
I have a YouTube channel. But I will send you. I will send you the link. I will send you the link.
Go and take action.
Hey, I will send on the platform. I will send on the platform. But when you reach there, you press the button of subscribe. I need 1,000 subscribers.
Have you had students?
Okay.
What?
Mubere bulungi.
You get them.
You get more than 1,000.
Are you sure?
Okay, teacher, we shall.
You guys, where was that work?
That was the exercise, the number teacher gave us.
Mwe ngate mugenda.
Teacher.
Yeah?
Teacher.
Yes.
Okay, what day work?
Work. You have not copied the work. You want the work? The one I was sharing.
No, I copied.
So you just try in your free time. You send me the solutions. Mugen, you go and take breakfast. And you hope your friends who have failed to log in. Please help them so much. The lesson is done. You're now having fun.
You're not going to end the meeting.
If I want, I can end. If I don't want, you should go. Okay, let me close.
Just end.
Okay. Okay.